Hello developers, let's start developing. My name is Veko and today we're gonna take on task 19 of the 2021 Advent of Code. And boy is it a hard one. It's not so hard as it's basically complicated. I went through it, I thought about it, and I'm still not sure what we're gonna do. I even wrote some code on the outside so to kind of test out some ideas, so I think I have a feeling of what might and what might not work. Means that we have a set of beacons and scanners inside our trench, and our trench is basically a 3D area, X, Y, and Z. So, for example, we have a lot of beacons, and the beacons are basically those that are going beep, 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 and doing nothing else. A scanner, on the other hand, can scan its surrounding area and detect those beacons. And the problem is, beacons have no idea where they are. So each beacon can, scanners have no idea where they are. Yeah, this part. Each scanner thinks it's the center of the universe, so each scanner uses its own 00 position as the 000, as the origin of the coordinate system. And the other issue is scanners have no idea where they are. So basically, if we have a big one scanner that is turned in this way, it will have an XYZ like this, and if we have another beacon that is that way, it will have XYZ coordinates like this. So they can be totally oriented in any random situation. So in that sense, for example, to illustrate this better, it would be like a person standing in Portugal and looking north. He's gonna say, well, Spain is to my left and the Atlantic is to my right, and I can see that France is above Spain. And a guy that is sitting in France, for example, and oriented south, he will say, no, you're wrong. Spain is below France. And that is because they are rotated away. And the important thing is that the scanners can only be rotated. So they don't know their facing direction. It can only be rotated, cannot be flipped. Why is that important? Well, basically there are, so to say, 48 different ways that we can orient 3D. Given 3 axes, there's basically 48 different ways how we can label them. That means because we have 6 permutation for that, we can have XYZ, we can have XZY, we can have Y XZ, we can have YZX, and we can have ZXY and ZYX. So each of these 6 permutations can be used in 6 different directions, because in 8 different directions, because X can be this way or that way, Y can be this way or that way, Z can be that way or that way. So this is a one thing that needs to be multiplied by 8, because those things are by definition independent. So we can have 8 combination of this, but not all the combinations are legal. Let's think of a 2D area, and if we have a point at 1, 2. I'm not too good at drawing, but let's say that we have this kind of thing, and of course I'm gonna use Excel to draw. Yeah, so if we have this point over here on this dot, if we rotate it, if we flip it, it will have the same y, but the negative value of the same y, the negative value of x. So any point xy will just translate to minus xy. But that is if we flip it. But if we rotate it, 90 degrees, this will translate into x will become y and y will become minus x. If we rotate it 180 degrees, it will always rotate to minus x minus y. And if we rotate it once more, it will be minus y x. And if we rotate it for a full circle, of course, it's going to become xy. So a point called xy doesn't matter how we rotate it, if we are not flipping it, can only have 4 of those 8 combinations. Because here we have actually 2 permutations only for 2. We have x and y and x. Those are the only 2 options, and each of these needs to be multiplied by 4. Because we can have minus xy, minus x minus y, x minus y. But we can see here that the, so to say, parity doesn't change. If we can consider, for example, that this permutation is even, because we need to do an even number of flips to kind of sort it. X is alphabetically before y. And this permutation, we can consider it odd, for example, because it will take one permutation to have it sorted. In that sense, so xyz will be even, and xzy will be odd. And I kind of noticed that when you're doing rotation, if you add up the number of minuses and the number and with the even or the odd situation of the permutation, you always get an even number. So that means that an even permutation will have 0 minuses or 2 minuses or 4 minuses for 4-dimensional things. So in our case, 0 or 2 minuses. And an odd permutation can only have 1 minus. Now, if we know this, then it's easy from this logic to determine what are the possible values. So xy can have 0 minuses, that's xy, or it can have 2 minuses, that's minus x minus y. And yx has to have 1 minus, so that minus can be here or it can be here. And these are all our 4 options. So we have 48 valid options, and we need to drill them down to 24, because exactly half of them will be valid. So I made this table. So these are the even and the odds permutations, and then I basically generated manually all the possible combinations. So we can have a plus or a minus everywhere, and these are correct because I made them manually, but I followed a template, or as we call it in a fancy way, an algorithm. So those we can determine all the possible rotations for a thing. And now, what we need to do. So we have, for example, we have this situation in 2D. So we have these 3 beacons, and we can have a scanner here. And this scanner will have coordinates for these 3 beacons, but relative to itself. And then we can have this beacon here. And the first beacon can have an coordinate system like this. And the second beacon, for example, has a coordinate system like this. And it will detect the same 3 beacons with the same 3 positions in totally different ways. And that's what we have. Now, the task itself. It says that all the beacons are overlapping. This is a continuous 3D region, so all the beacons are overlapping some other beacons. And all the scanners are overlapping some other scanners. And for any scanner, there is another scanner that has at least 12 beacon overlap with it. Which means that if we find if we find the 12 common beacons, we can determine the location of all of it. Yeah, for each of them. We can take one arbitrary scanner and say, well, you are in the correct orientation, doesn't matter where you are, and realign all the other scanners around it. Yeah, for example, we can say, well, you are by definition here, so the coordinates of these beacons are the coordinates of these beacons. And that is the task. If it sounds unclear and complicated, I think that's because it is unclear and complicated. So this is kinda sorta the minimal example that we can do. And the minimal example is 136 rows. This is the format of the input. And as always, let's read the input first and see where we get that. So the input, we will have a point interface, and I guess, yeah, this should be able to, come on, guess for us that we need to have an X and a Y, and yeah, we need a Z as well. And what is a scanner? Well, the scanner just has an ID interface that is a number, and it has a list of, come on, what did this do? And it has a list of beacons, which is an array of points. Now, we need to process this. Of course, first we're gonna need to read the lines. Yep, we read the lines, and we cannot do that. So now we have for each of these, and after having a lot of issues with parsing strings last day, now I will do this. I will just use a regex that says it can be more than one. Yeah, use this to get the scanner number, and don't worry. So yeah, this will be the result, and we return scanners. This will of course break our structure, so we need to say that yeah, we're using scanners, and array of scanners. So now we need to, yeah, let's do a while true. And let's have an index. So let's say something like line is lines of index, and then we need to, if we don't have a line, then we're at the end of the file, and we can just return the scanners. But if we do have a line, my idea is that we will parse this whole thing in one run of the while loop. So we need to line dot match the regex we're gonna have a match. If we don't have a match, we need to blow up. So yeah, this is the ID, and then we need to do while. Actually, we need to read the next line, and we need to do something like while line. But in order for that, we need to increase the index, and line equals lines of index, and that will be a let instead of a const. Okay, so while we have a line, read the next one, but with the one you have, and this is an array of points. We're gonna need to do this. Only I think we have no spaces between the numbers, so we need this. Map them and parse them and deconstruct them into an XYZ, and then we can just say beacons push this. It might work. One way to find out. This didn't work because we're never adding anything to the scanners. Yeah, even Copilot knows that we forgot that part. We had nice and fancy. So we have one beacon. Yeah, because we stopped on the empty line. Yeah, we need another empty line to skip the empty line. So now we're getting 4 things, but I don't see what's inside of them. I can always change how I display the input, and I think we only need one level more, because the default console printing, basically it prints everything up to some level and then it says okay, we're done. So we have our first beacon starting with 404, but we found it. Why is it 404? 459, 686, 649. Yep, and let's just see if the last ones are aligned. For the second one, 567, and the last one at all is, yeah, that much. Okay, that makes sense. So we have our beacons. Yeah, so what do we do now? I'm gonna take a detour, because we're gonna need to somehow be able to rotate a point. Yeah, we will need to generate all the rotations for a given scanner. So we have a scanner and we have all its points, but we need to say, well, what will the coordinates be if the scanner is rotated this way or that way or that way, without actually knowing what is the way. So we will need to have some kind of a thing that says rotations. That's an array of all the possible ways that we can rotate a point. So it will be a function, for example, the default rotation will be something like this. So it takes a point and it returns a point that is rotated exactly 0 degrees in any area. And then if we rotate it twice on X and Y, it will be this. Oh, actually this is a rotation. You can see these two are flipped, Z and Y. Something like that. So, yeah, actually this is the null rotation, so to say. So, how do I do that? Well, I'm gonna use this thing to generate my code, and I'm gonna use a fancy code generation tool called Excel. But in Excel we need to just say that let's have everything and just format it as a text. Because when you have want to paste a minus inside Excel, it says, oh great, you're starting a formula. No, we're not. So how do we generate code using Excel? Well, it's relatively simple. I'm just gonna delete the empty rows, verify that we indeed have 24, and I'm always saying Excel and using Excel, but don't worry, you can use whatever spreadsheet programs you have, and spreadsheet programs are very useful for things like that. So I will just now split these things. We have, for all of the cases, we have a plus or a minus, and we have the coordinate. So this will be left of this one, left of this one, and take 1, and I'm kinda stupid. General. When we format it as a general, it says, well, I tried to figure out what it is, but we said, even if I write a formula, it's text. Right of this one, and again take 1. So if we copy this over, it will update the reference. So we have, which will just say, well, do this for everything, do this for everything. Yeah, of course, that's X. No, actually, it's not. Do this for everything and do this for everything. And now I will go and take this thing that I need to do, and we can say it's this text, only it's not. We're gonna need to add this thing here, and let's see what the result is. So we have a plus X or a minus X and everything. So you know where I'm going with this. So if we just copy this, so instead of X we're gonna have the C column, and instead right here we're gonna have the E column, and right here we're gonna have the F column, and right here it's H, and right here it's I. So this is plus X plus Y plus Z. Let's run it all over the place. So for this case, minus x minus y plus z, minus x minus y plus z. Yep. And now I'm gonna do the magic of copy and paste. It's not that this part is hard to type, but to be honest, I'm gonna make a stupid mistake somewhere, and I'm never gonna be able to actually detect it. But now I know, and I verified this thing that it's okay. So if I know that that thing is okay, this thing is okay automatically. So we have all the rotations. And let's test this. So if we have a point that is x1, y2, z3, and we can map each rotations where call it with the point. So we should get an array of points. Stupid. It knows that point is an XYZ, but somehow it doesn't get that this is an array of functions that take a point and return a point. Let's see. So yeah, we are not getting an array of anything. So yeah, we are getting an array of points. Let's run that. We need to run the test method. One, two, three, minus one, minus two, minus three, 1, 1, 1, 3, 2, 1, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So we get all the 6 permutations and we get 4 items per permutation. Hopefully we're correct. So now comes the hard part. And as I thought about this, this might be by far the slowest thing that we're gonna do, because it has a lot of data. What I will try to do, and I think that I can envision how to optimize it if it's too slow, and I think it's gonna be too slow, but let's have a solution first. So I'm gonna define a reference as basically take all the beacons from the input and copy them over. This doesn't copy the actual beacons, so I will, for each point, give me the point. Yeah. This will create a dip. Actually, if we do that, we don't need this. I'm gonna take the first scanner and say, by definition, by fiat, this will be the correct one. So if that one is the correct one, that means that we need to match everything else according to that. And the problem with the task is that might not work, because in this scenario that is given, scanners 0 and 1 have an overlapping detection, but scanner 4 and 1 do not. Yeah. So we cannot just say here is 0 and match everything with 0 and we're done, because we're gonna need to have some kind of in-depth matching, because 0 overlaps with 1 and 1 overlaps with 4, so we can detect, if we detect where 1 is, based on that we can use that to detect where 4 is. So what I want to do is just make some kind of a, so to say, heap when we have all the data that we resolved already and use that heap, constantly growing heap of things to detect an overlap. And because detecting an overlap basically takes all the reference points, then that tends to be slow because it's at the very least a quadratic algorithm. Anyway, let's have it running. So let's take the first one as a target, so to say. Let's try to match something that we know matches. So we have scanner 0 and 1 and they are matching. So what I will need to do for each rotation, I will need to calculate the beacons. Yep. Actually, that's point, rotation of point, and this is the same thing that it wrote, but I want to have an arrow so that I can see where the arrow is. So those are all the beacons according to this rotation. The first rotation, of course, is the idempotent rotation. It doesn't rotate anything. So we have all the beacons in this, and we have all the reference beacons. And now what we need to do is we need to generate the difference, because the beacons are not matched. It's not the same set. So we will need to calculate basically every possible difference distance between them. So that's the reference beacon of reference, and for every target beacon of beacons, what is the diff? Well, the diff is a new point, and we actually don't need the absolute value, but I will remove it from the reference beacon to our own beacon. And we're gonna need to have a list of diffs. So we're gonna get a huge, basically reference count times beacon count, a huge list of diffs. And that's every point from the reference with every point from the beacons, from the target beacons, because we have no idea what is what. And now we will just group those diffs. Fortunately, I have a group reduce method. Let's use the group method actually first, because I might need to explain what I'm doing. So we need to group by a key. And now we have another problem, because we cannot use this as a key. Because we need to compare key to key in order to do them in the same group. So we either have to make a function that will know how to compare points, or a trick that I regularly use is basically this. If we have a point and we need to generate a key, that will be this. So we are generating the point into a string. And then of course we might need to point, but yeah, let's see if we actually need that to parse it the other way around. And I might use this key in a lot of places, so that's why I want to have it. So each div created to a key, and those are the keys, and have the groups, and then we need to determine, and this group by thing actually creates this kind of an object. It creates an array of objects that have a key, where the key is the key that I defined, that is a string in our case, and the items are actually the items that I've grouped. So we will need to filter out anything, any group where the length of the group is less than 12. So filter if it's bigger or equal to 12. Length g.items.length for that group. So if we detect such a group, that means we have our orientation. So if the group has a length of 0, then we need to continue, because we didn't get it. And now, since this kind of feels not too deterministic for me, I want to detect if we have a situation, and I'm hoping that we don't, because that would be devious, that we have two segments, two scanners that are right next to each other, but we have a third scanner that basically matches 6 of this one and 6 of that one, because then we will match at 12. But on the other hand, why do I care? That would be great. Because if we match 12 before we need match something on the other side, yeah, we're done. So that should be okay. Still, let's see if we have maybe more than one group. So if this is bigger than 1, then let's have this. Yeah. So right now we know that we have a single group. And that's our... We actually don't need the value. Yeah, we need the value. We have the value, and that value is... No, this is not totally not what I want. So we have a single group, and we have to say group of 0 dot items, and all the items are basically the same. Of 0, that's a point, group of 0 dot items of 0, and that will have... What doesn't it show? What is this inferred as? That the items are any. No, this is a point array. Now we got it. Because we initialized it without a type, and that's one of the issues with TypeScript, that when you are initializing an array, an empty array, it just cannot infer a type other than this will be an array. So oftentimes we will need to do this. We could have this as a single map or something like that, but it's just okay. So the scanner diff is this, and let's just console log it. can just and actually once we found the rotation we can just break out of this. Let's see what we get. If I'm not mistaken, not test, if I'm not mistaken, we will get that we don't have matches for a few of the rotations and then we will have a rotation. Match found for point blah 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 blah. Okay. So we actually found a match. What will happen if we try with the scanner 01, the scanner 4, which does not overlap 1? We should get that we don't have any such match. Yep, no match. And 1 and 4, which supposedly have an overlap. Yep. We needed to rotate quite a bit, but we found one. So what do we do now? Let's continue with 0 and 1. Yeah, just for interest's sake, what will happen if we try it with 1 and 1? It should run on the identity, match. And it's exactly, 1 is exactly 0 points away from 1. So I want to see what will happen. So now we have that. We have no match, and once we found a match we can break, hoping that there's only a single match. If there are multiple matches, we're screwed anyway. So we can basically say all the beacons, map them to to this. We need to basically, right now we have the difference in 3 dimension between the two scanners. So all the points that this scanner found, we will need to translate them, so to say, to match the original scanner. And I think that we need a plus. And now we need to just say, now we need to see, need to add this to the reference, but by definition there will be some duplicates. So we can say, okay, let's do this in the most inefficient way I know of. We can say, point to cute point. Let's create this, and we can do for each for of point of translated something like this. But if the ref keys includes, then we just console log that else we need add the point to the reference because it's not present in the reference. and that's gonna be all we need. Let's see if this works. Well, I have 50-50 chance that I messed up the plus and it should be a minus, but to be honest, it's easier to check than to analyze it. And we might have gotten lucky, or the input is weird. So let's see. These are the duplicates. I will separate them a bit. Because I think in the description there was a list of the matches or duplicates or whatever. So we have exactly 12 duplicates, which is the correct number of duplicates. And let's see. Have the overlapping detection cubes. These 12 beacons, they both detect relative to scanner 1. Since we already translated, this should be the relative to scanner 1 values. Yes. 537, 447, 404, 544, 528, 661, 390, 423, 345, and 357, 347. This is beautiful. So we have our new reference. So what do we do now? Well, now I'm gonna go again with the most inefficient algorithm I know, because it's the one that I thought of first. So what we're gonna do, we're gonna more or less randomly try. We're gonna we have the rest of the inputs in an array. Yeah, put the rest of the inputs in an array, and is not 0, do something. So we're gonna try repeatedly to match something to a reference, and basically since this should be a single, or what was the word, uninterrupted or continuous, single continuous 3D region. Well, each time we run through, we should be able at least to find one that we can add to the reference. So, for example, if the 0th is connected only to the 40th, and the 40th is connected to the 39th, and the 39th is connected to the 38th, what we're gonna do? We're gonna check from 1 to 40, and then add 40 to the reference. Then we're restarting and we're checking up to 39, and we're adding 39 to the reference. And so we're keep rechecking everything against our reference, and since our reference can only grow, eventually we will get to map everything, but that's definitely square according to the number of items. So it's not so hard for 4 items, because we will need to check 4 and 3 and 2 and 1, but for 1,000 items it might run for a while. And I don't think that these are quite easy objects, so yeah, it will run how long it runs. So while the rest is equal to 0, we cannot shift it, because we might not we are not processing it one by one as we used to. We're just trying, maybe it will be able to process. So we will need an index. So our index is 0, and const candidate, or not target, we used to call it, is rest of index. And now more or less all of this here. Now let's see what we need to change. For each rotation, so if we didn't found, this is the, yeah, here. So at the end we will just increment index, and yeah, this, yeah. But since we are just incrementing, this will be strict equals, and let it run into an endless loop when we manage to screw something over. So we're constantly looping through the same array, hoping that the array gets smaller and smaller. And in order to do that, basically when we find a match, we need to remove that. So over here, when we found a match, and actually I'm gonna yeah, no, that's not what I want. Found yep, found a match for that one. And let's have that. Found a match for that one. Let's see if it works. And if we did indeed find a match, yeah, this breaks is needed for the 4. Okay, but before we break it, yeah, we need to do this, and we actually need to do one thing more. We need to take one away from the index, otherwise we might end up skipping values. So if we are on index number 3 on the 4th item, and we have 5 items, so once we process and see that the 4th item is gone, if we remove it, the 5th item becomes the 4th item. So we need to go in move the index 1 backwards, so then when it goes forward, technically we don't want this to happen, but another way to avoid plus oneing something is just to remove one and then let it add one. So technically, yeah, we're doing the thing twice instead of doing it 0 times, but as they say, 2 wrongs don't make a right, but 3 lefts doing it make a right. Let's see if this works. It finished. What did it finish? Just a sec, I will remove these because we kinda don't need them. If we got into that part, it's okay. You can see, yeah, looking for a match for the first one. Found a match for the first one, that's okay. We're looking for a match for the second one, no, didn't find it. For the third one, we found it. And for the fourth one, we found it because everything from the first one is already inside the reference. Looking for a match for the second one, found for the match for the second one, and now comes the trivial part and the moment of truth. Reference.length, the number of unique beacons. here's hoping that it will be 79, and that is the correct value. Yeah, so let's see our puzzle input. So half a second for 4, and we have 33, so this will take about a minute, I would say. Found 1 match, 2 matches, 3 matches, 4 matches out of 33. And you can see that it's starting to get slower and slower as the reference gets more and more. Oh, it's starting to go really slow. And I lost count of how many we are looking for. So let's do this. Uh, Not index, but target.id. Yep. And the count of references. And let's run it. Over here. So we have 80 references so far. 92. Yeah, unless the input is terribly malicious, and it kinda is, actually, as I see it, because it seems that we have exactly that scenario when we have a lot of small scanners, a lot of scanners which are just connected to the one in front of them and one behind them. So you can see that it needs to run from 25 until 11. No scanner was a match for the current thingy. So we will need, I guess, to run 33 times through everything. And each time it will be slower because we're getting more and more references. And this part is looping through all the references and recalculating the same difference again and again and again and again and again, and I think that we might able to cache that. The calculation is trivial, so to say. It's just diff. But remaining 24. Okay, I'm off to get some water. This will take a while. Still running? I think I might need to go for a smoke. $20, halfway there almost. You can see that on one hand each processing is slower, but we don't have as much to process. And you can see we got lucky matching 19, 21, 25, 27, 33. And now starting a new. it won't get faster, it will just get slower, but I think it gets slower, yeah, quadratically, but we don't adding too many references, too many new references, so it doesn't get dramatically slower. We don't have 1,000 references or something like that. That would be no go. So these kind of algorithms are the worst because they are not. If you get a solution that will return values in 17 and a half years, of course you're gonna kill it and try to optimize it. But here we have a solution that will provide the values, but I think it will be something in the range of 4 or 5 minutes. So I have no idea whether to kill it and optimize it or not. Let's leave it for now. Let's leave it. But let's pause the video so it's just not me looking at a screen. So this thing finished in something like 5.5 minutes, and it says that the first part of the result is 425 and we have that many distinct references. Let's see if that is the correct answer. Hopefully it is, otherwise okay, great that it's the correct answer. We don't have to wait for it one more time. And now, okay, so for the second part we need to run it after we get the first part. We need to find out the Manhattan distance, and that's just the sum of the differences of the coordinates, a grid distance. Basically, it's called Manhattan because you need to go across blocks, and so to say, because you cannot just go diagonally, or taxi cab geometry or something like that. Anyway, this means that in order to get this we need the locations of the scanners. So I will do something that I'm not doing often. And yeah, of course, the solution is basically the same, so to say. I will copy all the solution and I will just put in a 0 here so that we run it just once, don't run it twice. Let's get back to the small example. Yeah, in the above example. So in the above example we're gonna need to have another array of points, which will be the scanners. And the scanners will need to have the first scanner as well, and the first scanner is by definition at x0, y0, z0. That's the distance of the first scanner. And then for each scanner, once we found it, well, the scanner is actually at the location scanner diff. That's where it is. Yeah, that's the differences, the diff between two scanners that are oriented in the same way and everything. So that's actually the distance between the origins. Yeah, so only thing that we need to do after we're done, we need to run basically another square for loop, but this will be for 33 items in the big example. So we're gonna have I1, and that is scanners dot length scanner 1, and we're gonna need, yeah, we're gonna get the second scanner. Since Manhattan distance is basically can go either way, it's the same, but doesn't matter from which scanner we're counting it. We can just, the maximum is 0, and yes, this is the distance between them. And then if the distance is bigger than the maximum is equal to the distance, and that's all there is. And we just need to return the maximum. So it's virtually identical with part 1, only we are looking for a different number. 3621. Yep, that's 3621. So, what can I say except see you in about 5 minutes. It started and it's going and it's going and it's going. So this thing finished in about 5 minutes, and it says that this is the correct answer. Let's see, we just need to copy it correctly, and let's see what is the largest Manhattan distance. Yeah, of course, that's the right number. And we have solved task 19 in, I have to say, a very inefficient and convoluted way. On the other hand, I have a feeling that we might need to have an even more convoluted way for the optimization. But that's a good thing, because that means we get to optimize this. And most likely that would mean getting a second video, because this has already dragged for a while. So talk to you tomorrow. Keep developing, and bye.